Cool. Yeah, so I'll go ahead and get started. This time we are going to be talking about learning from and for knowledge bases. And we will be talking about how to incorporate structural knowledge into NLP models and also how to use NLP models to extract structural knowledge from text. So knowledge bases are basically structured databases of knowledge. And there's a lot of different things that they can contain. For example, they would often contain entities such as which correspond to nodes in a graph, or relations, edges between the nodes. These are the most common varieties of a knowledge base. And there's also other knowledge bases, like there's knowledge bases of events or other things like this, which might also contain other things like who participated in an event or in what role they participated in, other things like this. But the most common examples that we have are things like entities and the relations between them. And so a couple of questions we can ask are, how can we learn to create and expand knowledge bases with NLP models, specifically neural models for NLP? And also, how can we learn from the information in knowledge bases to improve NLP models representations, or specifically neural model representations? And the reason why this is important is despite the fact that there's lots of text on the web, there's not everything that we would like to know is expressed in text, and also not everything we would like to know that requires something like complex reasoning, like the stuff that we talked about in the semantic parsing classes, for example, is easily accessible through textual format, even if it is written somewhere. So we answered the question of how can we use structured knowledge to do things like answer questions or do symbolic reasoning in the semantic parsing class. But behind this symbolic reasoning, you also need to have a database of knowledge that can support it. So that's the point of this class. So I'm just going to give a few examples of knowledge bases. So one very classical knowledge base, WordNet, was created for a long time. 1995 is just the date of the report that I cited here. It actually started creation a long time before that. And basically what it is, it's a large database of words, including parts of speech and semantic relations between them. So the most common relation is a hypernym-hyponym relation, where a hypernym is kind of like a higher level concept and a hyponym is a lower level concept. There's also other relations like something that's called meronymy, which is something is a part of something else. So you might have like a steering wheel as part of a car. You might also have opposites. So like hot and cold are opposites, or good and bad are opposites, for example. And so this was a very big effort. Yeah, here are some examples. So there's is a relation, part of relations, type instance distinctions. So a Toyota is a type of a car, for example. Verbs are ordered by specificity. And this was a major effort. It took years and years to create. It was created in many languages. In fact, last time I went to the WordNet site, it said, unfortunately, we cannot expand WordNet anymore because we don't have money to do so. So that kind of gives you some of the practical issues with creating these knowledge bases entirely by hand. Another example of a classic knowledge base that was even more ambitious, perhaps, than WordNet is something called Psych. And it's basically a manually curated database where it attempted to encode all common sense knowledge that a normal person would have, basically. So this would include all of these different types of knowledge, including things like social behavior, law, organizational planning, organizational actions, plants and animals, ecology, living things. And then these would be kind of, at the very top, you have the most most general knowledge, like about things. Then you have spatial reasoning, and things like this. And this was, a very ambitious project, and it did get somewhere. But the issue with this is, if you're trying to encode all of these things, what is the representation language you use for it? How do you ensure it has appropriate coverage? How do you handle exceptions to your world knowledge and things like this? And because of this, I believe when I looked this up about 4 or 5 years ago, they were talking about their first practical application of this knowledge base, 25 years after the project started. So again, there's lots of things that you can encode through symbolic knowledge and stuff like this, but it's a very laborious task. However, there certainly are some things that in psych that would not be handled well or consistently by a language model, for example. Yeah.
One of the things about psych is that they have a lot of trouble kind of like making things consistent and rational and not having implode by having inconsistency.
Yeah, and that's another thing. So how do you make things consistent and rational? Another thing is, how do you deal with the fact that something is true most of the time, for example? So we expect this to be true most of the time, 80% of the time, 90% of the time, but how do you incorporate that in a reasoning process, for example? So a little bit later in history, we go to about 2007, there was a very big revolution in how we structure knowledge, namely Wikipedia. And Wikipedia is encyclopedic knowledge that's available online for free. And most of it's in textual format, but it also has these things like info boxes, which are structured data that tell you about relations between things and other things like this. And the good thing about it is that all of this is manually created, but it's on such a massive scale that it gives you something that just wouldn't have been possible if you were hiring people to do this kind of curation, I guess. And there's also kind of the schema information over here. So it's like if something is a university, these are some fields we would expect the university to have. Like we'd expect it to have things like former names, mottos, types. These former names are also annotated with years. So it gives you some idea of temporal information and other things like this. So this is a really rich knowledge source that wasn't available before. And several iterations later, this structured knowledge base is a thing like, can turn into a thing like Wikidata, turned into something called Wikidata. It was called Freebase for a while, and then Freebase was rebranded as Wikidata. And Wikidata is essentially a very large knowledge base, curated, large scale, multilingual. This is an example from Richard Feynman that has, things like types, also known as gender, date of birth, place of birth, country of nationality. And this is pretty extensive. And in things like this. And I actually, in preparing the materials, I checked to see what Wikidata knew about me. And it knows my English name, my Japanese name, that I'm human. Pretty good, I didn't know that before I looked it up on Wikidata. Male, given name, that my occupation is university teacher, computer scientist, researcher. I work on natural language processing. I graduated from Kyoto University and University of Illinois, Urbana-Champaign. My advisors were this thing. And I actually don't know where it got all of this data. It does tell that it got this data from the Mathematics Genealogy Project, which is a kind of a structured database. So it's basically pulling in information from a lot of different sources. So this is now kind of the standard go-to database. I had a question on Zoom. Can you give some examples of knowledge captured by Psych that an LM cannot learn? So to clarify, an LM, I don't think there's anything an LM cannot learn. And kind of like by definition, if we think of a neural network as a universal function approximator, an LM can learn anything with a sufficient amount of data. But the things that LMs are not able to learn easily, for example, that would be included in a structured database like Psych would be, I don't know, spatial reasoning. You know, if we have one box with a size, an edge size of 1 meter and one box with an edge size of 3 feet, which has larger volume. That would be something that I wouldn't expect an LM to get right consistently, but it would be easy, very easy from something like Psych's spatial reasoning capability. Another example is that actually language models, even really large language models, are really not all that great at capturing factual knowledge consistently, including the type of knowledge that's included in Wikidata. So that's another example. It's not that they can't learn it, it's just that they don't reproduce it very consistently. Any other questions? Okay, cool. So I'm going to talk about a couple relationship, things about the relationship between knowledge bases and modern NLP models. And one big issue with knowledge bases is that despite the fact that they tend to have very high precision, especially the manually curated ones, they have low recall. So there's lots of facts that aren't included in them. And to give an example, in Freebase or Wikidata, 71% of humans were missing a date of birth, where probably all humans have one of these. My entry did not have my date of birth. I might be happy about that, but yeah.
Well, some people don't know their date of birth.
Some people don't know their date of birth, but that doesn't make the knowledge base any less incomplete, right? Yeah, it's true. So a very common NLP task is called relation extraction, which basically tries to extract relations between entities and values that correspond to them, like things like date of birth or other pieces of information. Thinking a little bit more broadly, this can also be called information extraction, and information extraction in general is basically any sort of taking unstructured text and trying to extract structured information from it. So there's a number of different ways that we attempt to perform relation extraction or attempt to extract information from models. One way that this is done is by looking at the consistency in embedding spaces and trying to infer relations from this. Another way this is done is trying to extract textual information, like structured information directly from textual information. And I'm going to be talking about both of these in turn. So if we remember from the past several classes, we talked about how in embedding spaces, there's consistency where, for example, if we subtract man from king and add woman, we get queen. So this relationship of like man to woman or uncle to aunt or king to queen is basically a gender relationship, going from a masculine a noun with kind of masculine traits to a noun with feminine traits. But it could be any other variety of relationship between words or entities, right? Notably, in WordNet, I talked about several relationships that were manually included in the database. This is not one of the ones that was included in the WordNet database. So this is an example of something that you could not easily get from WordNet, but you would potentially be able to get from something like word embeddings. So one example of this is if we take regular word embeddings. So these would just be embedded, like one embedding per word or one embedding per entity. You can run a model over them that basically tries to exploit the regularity in the embedding space to try to extract relations that we didn't know about before. So we basically have a model that takes in two embeddings, embedding 1 and embedding 2. It multiplies each of these by a weight matrix. So you could also view this as like concatenating these two embeddings together, running them through a nonlinearity, and then making a prediction. So it's like an NLP that decides based on the embeddings whether a particular relation exists. There was also a model called the neural tensor network that adds bilinear feature extractors, which do the standard kind of MLP-based thing, but they also have a weight matrix here that you multiply with E1 and E2. And the reason why this might be good is, like, let's say if these two vectors were more similar, they could be judged to be in a synonym relationship or to be in the same semantic class. If that's the case, to measure the dot product between E1 and E2, all you would need to do is make this be the identity matrix, and then this would be equal to the dot product between the two vectors. So basically, this is an easier bilinear models like this. This is called a bilinear model where you have a vector, a weight matrix, and then another vector. Tend to be better for expressing things where it's like these two vectors are similar, so we want this to be true, or these two vectors are similar after some linear rotation. So we also use these in attention as well, if you remember. So this is a powerful model for deciding whether two embeddings indicate a relation between two words. And sorry, you have a question? Given that this was pre-contextual embeddings, does this approach disregard the intervening language context? If so, how well does it do? Yeah, so that's a very good question. This is often used for embedding entities, and when you're talking about entity embeddings, the names of entities are, the way they created entity embeddings was often by kind of linking the entities to a database and then learning the embeddings over each of the entities. So in a way, the contextual resolution part was done before learning the entity embeddings. I don't think I covered these methods in the slides, but just to give an example of how it works, let's say we have something like, I'll just use the example I had before. So Graham Neubig is a professor at CMU. You would run an entity linking model that would connect this to the entity in Wikidata. So basically, this would be linked to some Wikidata ID like Q52794. And then this would also be linked to another thing in Wikidata, Q32148. And then you would learn embeddings of each of these entities, either from the knowledge graph itself or from text. And because of this, you'd have these embeddings of entities, and that those are more invariant than like a contextualized representation, I guess. So yeah, sorry, that was a detail that I glazed over, but this is actually pretty important if you're using these kind of relation extraction models between entities. So, and then a follow-up question is, I guess this subscribes to the idea that E1 and E2 having a relation in between them is always true. So I guess to rephrase the question, this can't take into account like temporality, like it was true for 5 years, but then it wasn't true anymore. Like people got divorced or something like that. People were married, but then they got divorced. Yeah, it isn't easily able to take into account things like temporal relations, I guess. Any other questions? Okay. So another way that people did this was, actually, I have an example here. So this is how you can learn embeddings from knowledge graphs. It's not how you learn embeddings from text, but basically you have an embedding for each entity in the knowledge graph, and you have an embedding for each relation in the knowledge graph. And what you want to do is you want to take the embedding of the head entity and the tail entity and add a embedding for the relation between the two entities, such that entities that are in fact inside that relation are close together, and entities that are not in that relation are far apart. So if we have an example where this is one example of a head entity, this is one example of a tail entity. This is in the employment relation. So you would have like Q52794 employed by Q32148. And then you would have another example, which would be, you know, Barack Obama is not employed by Harvard, or something like that. And that would be your negative example. And then you'd want to make the score of this higher than the score of some negative example. And this, this has one vector for each relation. So it's just an additive vector for each relation. It's intentionally simpler than the neural tensor network. And the idea being that you want to have a space that's kind of consistent linearly like this. And there's a bunch of modifications to make these models more complicated and sophisticated and things like this. But this is the basic idea here. And this can be learned without any text. It can be learned directly from a knowledge base. So you just have a big knowledge base, and you train it based on the entities in the knowledge base, the relation between them, and you randomly sample negative ones. Yes. Yes, it does. Yeah, so that's a relation. Cool. So these are some examples of how we can learn knowledge graph embeddings or other things like this. We can also learn relations directly from text. And basically what we want to do is we want to identify text that is indicative of a relation. So this, or no, actually, I'll still leave this up there. So we have text like this. We can identify the entities in the text. And we then want to get a new text that has two entities in it. And based on that text, identify whether that text is indicating that that relationship exists. So like, let's say we also had something else, which is like GN was fired by CMU, which I hope will not happen. Does this indicate that somebody is in an employment relation or something like that? It kind of indicates that they were, I guess, which is a difficult case. And so we want to take a sentence that has multiple entities in it and decide whether that's indicative that we should be adding an edge to the knowledge graph. And so the most common way to do this is to start out with a knowledge base that has a whole bunch of these relationships, like Wikidata, and use distant supervision or weak supervision. And what we do basically is we find a few examples of the entity, and we find examples of the entity and the other entity, And we look up a whole bunch of sentences that include both of these. And add them is essentially positive training examples for this relation classifier. And here, with Steven Spielberg and Saving Private Ryan, the relationship is producer, or director of. And we can see the second one very unambiguously indicates that Steven Spielberg is the director of Saving Private Ryan, whereas the first one does not unambiguously indicate that Steven Spielberg is the director. But nonetheless, this would still be added as a positive training example. So this is a very cheap way to create a large corpus of kind of like noisily annotated data. Yes. So that's a good question. Basically, you just don't worry about it, and you kind of hope that the positive examples that are actually positive will overwhelm the number of examples that are not. You know that's wrong, but you assume it anyway for the purposes of training, basically in this paradigm. In a slide or two, I'm going to talk about ways that you can further improve this. So this is a very common way of training relation extractors, and then we basically need a model to classify them. Actually, I realize, I had some slides about CNN, how you do this with CNNs. Now you just do it with BERT. So I'll skip the slide here. Basically the idea is you throw the sentence into BERT and you classify it as being true if it's one of the sentences that where two entities are in a relation. And again, you use negative examples that are to an entity that is not in that relation. And you use the sentences with entities that are not in that relation as negative examples. However, there's other interesting things that you can do in addition to just throwing text at BERT. You can also annotate. Sorry, this is another example of that. Yeah, so sorry. The more interesting examples are at the end of the presentation, so I'll talk about them there. For now, BERT solves most of your text classification problems, so you don't need to worry about those ones. Okay, so the next part is, what do we do when the training is noisy because we're making an assumption that's obviously incorrect, which is that all sentences that we have with the two entities are positive examples. So this isn't true, but we assume it's true to generate training data. And one paper that I thought was pretty interesting as a way to do this is basically what they do is they have a small cleanly annotated corpus where they've actually asked people to annotate relations and say, this sentence is definitely indicative of this relation. This sentence is definitely not indicative of this relation. And you start by training a model on that data, or you do multitask learning where a model is trained on that data to actually make predictions. But then on the big noisy data, you also have this transition matrix. And this transition matrix basically transforms your predicted distribution into the observed distribution over the data. And so what this means is, like, you might have predictions like, I think this is in these two entities are in the employed by relation. These entities might be in the president of relation or director of relation. And you have this big transition matrix that basically models the noise that you might have. So if your model predicts employed by, it might be actually not employed by some of the time. So you downweight the probability of employed by, or if you predict employed by and president of and director of, it basically will say, now I'm more confident in employed by because it's predicting these multiple instances here. So by jointly learning the kind of clean predictor and the noise distribution, you can handle this, this noise. And they add some control over this transition matrix, because if we made the transition matrix like be allowed to be anything, it wouldn't have an appropriate bias that the model should be right at least like some of the time. So they have something called trace normalization that basically tries to make this matrix close to the identity. And the more normalization you add, the less noise you're assuming in the actual output. Yeah, and this is what I said before. So anyway, this is a really good way to extract knowledge from data. I assume that some of the things in Wikidata are at least seeded by a model like this, where they crawl a whole bunch of data on the web and they propose potential additions to Wikidata. Yeah, that's something good to know about. Are there any questions about this? If not, I will change gears and move to taking knowledge bases and using them in neural NLP models. Okay. So the first thing I'd like to talk about is how to use existing data sources, existing knowledge sources, to improve embeddings that we already have. This was first used in non-contextual embeddings, but I think the basic idea is interesting and worth thinking about from the point of view of contextual embeddings as well. But basically, the way this works is we have a data set from which we can learn embeddings, or we have a set of embeddings. And then we also have a knowledge base that specifies particular relations. And what we do is we take these embeddings and we post hoc convert them into something that's more congruent with the structured knowledge source that we have. So unlike doing something like jointly learning embeddings together with some sort of loss based on the knowledge base, this allows you to basically retrofit the existing embeddings into something that works together. So the specific objective function that they used to do that was this. So if we have qi, which is an original embedding, and qi hat, qi hat, which is the original embedding, and qi, which is an ingested embedding, they have a dual objective of keeping the embeddings as close as possible to how they were. So they have this loss function where the higher the distances between the adjusted embedding and the original embedding, the more the loss is. And then we also have something where they take all embeddings that are in a synonym set. So this is something you can get, for example, from WordNet. It's a list of all the embeddings that are synonymous. And all the embeddings that are synonymous, you try to make them as close together as possible. So you're trying to minimize the distance between embeddings that are in the synonym set and while simultaneously not changing the embeddings. Maybe more interestingly, this can also be used to do things like force antonyms away from each other. So one problem with kind of learned embeddings is that things that are very different, that are actually very different things, if they appear in similar contexts, they tend to get related embeddings more or less. And so things like love and hate, good and bad, hot and cold, will tend to be appearing in similar contexts, so they get very similar embeddings. It's also actually true, and maybe even a bigger problem for things like question answering, that many entities get put in a very similar space. So if you look at the nearest neighbors of something like Smith, there'll be things like Johnson or Craig or other kind of like stereotypically English last names. And because of this, you get a model that thinks that John Smith and John Johnson are nearly the same person, and that's not all that great for a QA model, for example. Okay. Any questions about this? Okay, so this is for any sort of embedding model. It can be used on non-contextualized embeddings. It could also be used on contextualized embeddings if you want to do things like alignment between contextualized embedding spaces across languages or stuff like this. I don't have any slides on this, but this is also something that people do. Another way that you can use structured knowledge is by injecting knowledge into language models. And this is something that I'm actually pretty excited about from the point of view of improving, factuality of language generation or things like this. This cited paper here is one of our papers, but there's also other papers on this topic as well. So basically, the way we did this is we provided LMs with knowledge in the form of graphs, where you can copy things from individual relations in the graphs. So each text is given, or each text to be generated is basically given a relevant knowledge base taken from Wikidata. And we examine all possible decoding paths that could allow you to generate the text. And the important thing here is normally a language model does only word-based generation, right? So it generates, if it wants to generate an article about Obama, it would have to generate Barack Hussein Obama II, born August 4th, 1961. And when it generates these, it would generate that word by word. However, in this particular model, we're given a knowledge graph where we have our main entity, which is Obama. And then we also have things like birth name. We have things like given name and family name. And each of these have their own nodes here. And the idea is that the language model at the very beginning, it could generate the next word Barack, but it could also generate the kind of like birth name pseudo word. And in doing that, it would then be able to generate all four of these words all at the same time. And it would be able to do so with relatively high confidence because it has a structured database that tells you that Obama's birth name was Barack Hussein Obama II. So the reason why I think this is good is because basically this allows the model to choose to not actually generate, facts from scratch just from its parameters, but actually rely on the structured knowledge within the language model to allow you to kind of generate this with higher confidence. And notably, this is also adaptive. So if you change the entity of focus here, of course, the birth name would also be changing. So if you generated the birth name node, you would get a different surface form, but it would still look like a very similar generation graph. Cool. So I see a question on Zoom. Can we use this is, I think, for the last slide. And the question is, can we use something similar to improve pre-trained embeddings such as fast text for a specific domain? Yes, I'm sure you could do it for a specific domain too if you had a domain-specific knowledge base. Domain-specific knowledge bases do exist for some domains like biology or medicine or things like this, but there aren't as many. There aren't necessarily a whole lot of them that are available in easy to use formats. Cool. Any questions about this? Okay. Cool. So another piece of work that I have worked on previously and I'd like to introduce now is you can also kind of combine the ideas of textual reasoning and knowledge bases. And one of the good things about knowledge bases is you can do things, and I'm going to talk about this in a second, but you can do things like reason over paths between entities. So you can easily ask a question like, where did Barack Obama's daughter go to school? Or something like this. And then what you do is you follow the the daughter or the child node, and then you follow the educated at node, and you get the answer. But if this is something that's not included in your knowledge base, obviously you can't answer the question. So we have also had some work where we basically combined these two things together. So we had a text corpus where we match mentions of particular entities. And the way this works, this is a very kind of expansive figure, but the basic idea is that we have a question: when was the Grateful Dead? When was the Grateful Dead and Bob Dylan's albums released? And what this can do is this can look up entities in a knowledge base. It can expand the location of all of the Grateful Dead entities and the Bob Dylan entities, and find the locations in a big text corpus, look up all of the mentions, aggregate the mentions to entities, and then go back and do a second hop where we start with these entities and further look up mentions to find things like the answer to the question. In this particular example, we don't have the answer to the question here, but basically the idea is it's a way to do multi-hop reasoning over textual mentions. And in order to do this, you do the sort of relation extraction that we talked about in the previous thing here, which allows us to identify, which sentences mention a particular relation. This can be done kind of in a discrete, like multi-hop setting where we do text-based question answering, but this also allows you to do it in kind of a continuous end-to-end differentiable manner. Okay. Yeah. How do you decide how many hops? That's a good question. I believe, if I remember correctly, we limited it to 2 hop questions. That's a good question that I haven't thought about since I worked on this a couple years ago, and it was Buan who was the main author on this, but I think it was only limited. No, here the answer is actually an entity. So what you want to do is you want to do a hop and then another hop and find the entity that actually answers the question. Cool. Okay. So up until this point, I talked a little bit about relation extraction, where we have a fixed set of entities like birth name, given name, family name. So basically, if you want to extract all of the relations that you have on Wikipedia, Wikidata or something like this, you need to know what the relations are. You can create distantly supervised data by looking up all the entity pairs that have that relation and then train an extractor for each of the relations. However, there's also something called open information extraction. And open information extraction, the basic idea here is that we don't know a priori what types of relations we'll want to be extracting between entities. So rather, we just use the textual description of the relationship as the relation itself. So if we have a sentence, United has a hub in Chicago, which is the headquarters of United Continental Holdings, the relation would look like United has a hub in Chicago. So this is good because maybe there's not a has a hub in relation in like Wikidata or something like that. So you would want to be able to extract this information. In Chicago is the headquarters of would be another example. But the problem with this is that this does not abstract well. So if we have Chicago is the headquarters of United Continental Holdings, we will get a very similar relation. Chicago, United Continental Holdings is headquartered in Chicago, and that would be treated as something completely different. So basically, and I'll be talking about how to solve that in a second. So in OpenIE, the most common ways to do this, because the idea is relatively simple, the most common ways to do this are rule-based OpenIE. And basically, they use a parser to extract this information according to rules. So a relation must contain a predicate, the subject and object must be noun phrases, etc. And then you just extract everything that corresponds to this. And you can train a fast model to extract over very large amounts of data. And you can aggregate multiple pieces of evidence heuristically to find common and therefore potentially reliable things. So, you know, if something is mentioned lots and lots, then it's probably more reliable than something that was only mentioned once. There's also neural models for OpenIE. Because heuristics are still not perfect, you can get things like parsing errors, or you can also you can have issues with things like uninformative relations like is going to, or other things like this, which are just not very useful. And one interesting thing is you can actually create relatively large data sets for this by asking things like simple questions. So this is like a question answering based OpenIE system. And you have UCD finish the 2006 championships as Dublin champions by beating St. Vincent's in the final. And you ask questions about finished, like who finished something, what did someone finish? What did someone finish something as? How did someone finish something? And this allows you to extract relations like this. And these are, this is actually called QA-SRL. It's question answering based semantic role labeling. So this is saying like, who is the agent of this action? Who is the patient of this action? So agent is kind of like subject, patient is kind of like object. And then other kind of semantic frames like this. And you can convert these into OpenIE based extractions. So you can say like who head finished tail as, and other things like this. So by doing this, you can get something that's, you know, a bit more clean. You won't be picking up lots of garbage things that people think are not, you know, real pieces of information. Cool. Okay. So another topic in knowledge, kind of knowledge base construction is learning relations from relations. And there are certain things that you can infer precisely based on particular pieces of information you already know. Like, for example, the child of a child is a grandchild, is something that holds every single time. There are other things like, there are other things, another example would be like, is the CEO of, entails is employed by, right? So there are other things that you cannot necessarily, are not true all the time, but hold a lot of the time. So like, is the founder of and is employed by are pretty common relations. Is the founder of, is the president of, or is the CEO of is also a common like relation that holds some of the time, but not all. So one thing to note is that word embeddings give information of the word in context. And these can be indicative of KB traits, but other relations or combinations can be as indicative or more indicative. So it's a link prediction problem in graphs. And one very common way of solving these problems is through tensor decomposition. And the way it works is basically you model relations by decomposing a tensor containing entity relation entity triples. So if you have a entity on the left-hand side, I think AL stands for left-hand side, an entity on the right-hand side, and then relations between them, you basically fill all of the places with relations in between them with ones, and then you try to predict where the other ones would appear in the tensor. And interestingly, this is what Ilya Sutskever did before he, was making sequence models and things like that. So I didn't know this until I found this paper when doing the survey to create the slides. So that was kind of funny trivia. Cool. So this is a common technique. So basically, you take all the relations you already know and you try to fill in the other ones that you you don't know with relation matrix completion or tensor completion techniques. One other interesting thing that you can do is you can do this to reconcile schema-based and open IE extractions. And I really like this idea a lot because what we do is essentially we have all of the relations that are included in Freebase or Wikidata. We have all of the relations that are included in another database like TAP. We also have lots of open IE extracted relations like professor at, historian at, and things like this. And we do a tensor completion where we basically say, well, if we know this relation existed in the OpenIE database, we can fill in the other relations that we expect to be true in the schemas that we have. So this thing to be able to do because it also allows these very like non-generalizable OpenIE extractions to be generalized into something more useful. Named relations and things like this. You can also learn like the correlations between things in OpenIE. But yeah, so basically this gives you the ability to fill in things that you don't know. Okay. Any questions about this? Okay. So another interesting thing is this allows you to kind of, on a high level, reason about the correlation between one or multiple relations in a particular schema. Another thing that you can do is model relation paths, and multi-step paths can be informative for indicating individual relations. So this is a paper that basically is looking at a citation graph, which is like this paper cites this paper appeared in this journal, or other things like this. And the one task that they try to solve is, given a particular word that appears in a paper title or something like this, recommend the venue in which to publish the paper or which to submit the paper. So if you say, and what they do is they learn these like multi-hop paths and try to predict which venue the paper would appear in. So they have things like the word appears in the title of a paper and the paper is published in a journal. So this is the most, direct paths. So if that word tends to appear in a paper title that appeared in the journal, then that's a good indication. However, you can also learn other paths, like the word has appeared in the title of a paper, where the first author of the paper is the first author of another paper that appeared in that journal. Or the word appears in the title of a paper where any author has a paper that appeared in that journal, and things like this. So I think this is pretty interesting. It's actually a pretty simple technique of expanding paths and then learning features over those paths. But it kind of shows the power of having a structured representation as opposed to, some other type of representation over only text, for example. This was taken even a step further, where there are basically, you can consider whole paths in a differentiable framework. So you assume a logic rule, like the first order logic rule that I was talking about before. So this is has office in city and country, implying has office in country. So it's the same type of path, basically. And what they do is they treat the path as a sequence of matrix multiplies where you have a particular rule weight. And by summing over all of these potential paths between logic rules, you can then essentially infer the probability of this rule being true, given that these other rules are true. And one good thing about this framework or other, similar frameworks like it is, as I mentioned before, there's lots of kind of knowledge that you could use that is true a lot of the time, but not always. And this is a way where you can incorporate kind of things that are sometimes true, but not always true. There's other frameworks for this. Like there's something called Markov logic that was very popular for a little while, which basically gives logic rules weights and then tries to reason over them. This is just like the simplest instantiation that I can think of this. But if you want to go down this rabbit hole and learn about like differentiable reasoning, there's lots and lots of other papers. Yeah. These are not manually created. These are expanded exhaustively, and then you have a learning model that tries to learn basically a linear model to upweight the scores of rules that are very indicative that a particular paper would be published in a journal, for example. So yeah, this is definitely a learning framework that does this. I had a question on Zoom. Could I motivate the importance of learning relations from relations again? Is this more like expanding the knowledge base or chaining existing knowledge? I guess you could call it both. It's because knowledge bases are always woefully incomplete. We will want to be filling in the missing parts. And one very effective way to fill in the missing parts is by inferring things that are often or always true based on the other things that we already know. Another way to do it is by looking up text and doing relation extraction or something like this. So I think both of those are, they both need to be used to get the most complete view of the things that you already know, like extracting new knowledge from unstructured sources and inferring what things you should know from structured sources using logic. Cool. Any other questions? Okay. So I'm going to wrap up by talking about probing knowledge in language models. And basically what we've done up until this point was I talked about how to extract knowledge from text and also how to incorporate knowledge into language models and how to extract knowledge from the other knowledge we already have. This part is more about trying to figure out what knowledge language models have access to. And we talked a little bit about this in the prompting class, but I'm going to talk about it in a little bit more detail here. So traditional question answering and machine reading comprehension models refer to an external resources to answer questions. But we'd also like to know, do LMs pre-trained on large text corpus, on a large text corpus already capture the knowledge that might be available in a text corpus? And the most famous work kind of examining this is this llama corpus or this llama data set. And basically the way this data set was created was by taking an existing knowledge graph and coming up with a textual query that that indicates this relation. So if the relation is born in, we come up with a query Dante was born in, and you mask that out. And then you have the language model try to answer this query. I think this is an interesting way of telling whether a language model has access to particular types of information. One thing I do not think this is, like a lot of people maybe misunderstand the motivation for this work or assume that language models are better than they actually are. I don't necessarily think this is a good way of constructing a knowledge base, because to be honest, language models are pretty poor at this task. They're not very good at recalling, pieces of factual information that they only saw once in a text. They're also not particularly good at kind of abstracting things out and like identifying pieces of information based on like paraphrasing other pieces of information they already have. So despite the fact that I've worked on this problem, I don't think this is like necessarily the best way to be like constructing your knowledge base, for example. But anyway, I do think it's interesting to be able to tell whether a language model is able to recover particular varieties of knowledge. And so the llama benchmark includes manual prompts for 41 relations. These come in the form like X was founded in Y. You fill in the subjects and you have the LM predict objects like Bloomberg LP was founded in Mask. The accuracy was something like 31%. However, there's a big caveat about this, which is that they only predicted words that could be predicted in one subword token. So things like Chicago or London or Toronto. They did not predict things like United States or New York or things that require multiple tokens. So actually the llama dataset is a lot easier than it would be if they included these multi-word entities as well. So BERT actually probably wouldn't be able to do anywhere near 31% if it was predicting these. Oh yeah, hardly any companies are founded in New York or San Francisco for that matter, right? So we don't need to worry about them. Interestingly, the born in relation, France is by far the most common country because there aren't very many countries that have only are only a single word or only a single token, and France is the most common one. I'm not sure why Germany wasn't in there, but United States, United Kingdom, and other things like that. So yeah, it's interesting. So we also created a data set that is cross-lingual. So it allows you to probe factual knowledge in cross-lingual LMs. I know some groups in the class are looking at this as a project. Here, the English accuracy is lower than the Llama benchmark because here we considered multi-word entities. And the way we do this is basically we use some decoding strategies for multi-word, like masked language models, where you predict like one token and then predict the next token and then predict the next token, et cetera, et cetera. So here, I think this is probably a more faithful guess of how good language models are at predicting, and it's only, you know, about 17% accurate here on English. On the other languages, you see varying accuracy. Spanish is up to 15%, all the way down to things like Bengali, Yoruba, Ilocano, where we have quite poor accuracy. One thing that I think is kind of interesting about this is if we think about how language models work, the facts that are included here are pretty uniform across the different languages. And for example, in English, many of the facts in English are, or many of the facts in the other languages are also included in the English knowledge because registered. So the fact that the accuracy is so bad on the other languages doesn't indicate that a language model doesn't, quote unquote, know the information somewhere in its parameters. It only indicates that it was not able to retrieve the information in the other language, which I think kind of makes this an interesting challenge in that, like, how could you better elicit information that the model already knows if you asked it in English? So I think that's kind of an interesting thing about this. So another thing is a closed book QA from using language models, and this can be one of the examples of a type of closed book QA that can be done with language models is answering these sort of factual questions. And so you can say, like, when was Franklin D. Roosevelt born? And the answer is 1882. And there are papers on trying this with pre-trained models. However, if you compare kind of closed book models that try to answer these factual questions, the type that we see in knowledge bases, models that have access to retrieving queries tend to do better. And actually, this is over the natural question data set. But I think for the factual queries that we're talking about here, actually the difference is quite a bit more stark. So basically, if you look at the best closed book models, how well they do on retrieving factual knowledge, like relationships between entities and stuff, it's just kind of a lot worse than a model that's able to look up answers on the internet or answers in Wikipedia or something like this. So I think this is indicative that studying both frameworks, a framework where you have a language model that just uses its parameters to answer these factual queries, how can we improve these models and make them better at doing that? And then at the same time, also, how can we come up with the best models that are able to, like, look up facts on Wikipedia and answer questions appropriately? Are kind of both interesting topics. Cool. So yeah, that's all I have for today. We're a little bit early, but I think that's fine. Any questions?